Imagine for a second a dormant volcano sitting right in the basement of a building you work in.
Right.
You're taking this highly combustible fluid, pumping it through the exact same structure where people are sleeping or working, and you're atomizing that fluid and setting it on fire on purpose.
Which sounds completely insane when you put it like that.
It really does. Because usually when we talk about mechanical design, there's this expectation of, like, invisibility. You turn a thermostat on the wall, the room gets warm, and you just never think about the actual beast of a machine roaring away down in the mechanical room.
Absolutely. It's out of sight, out of mind for most people.
Yeah, but today we are doing a deep dive into the rules that keep that beast in a cage. We are opening up NFPA 31. That is the 2020 edition of the Standard for the Installation of Oil-Burning Equipment.
And it's quite a document.
It is. Our mission today is to understand the invisible, frankly blood-written rules that keep all that contained chaos from just burning the structure to the ground.
Blood-written is honestly the best way to describe it. It truly is a map of past disasters.
Yeah.
Oh, for sure. Every single clause, every exception and table in NFPA 31 exists because at some point, somewhere, a system failed catastrophically.
Someone learned the hard way.
Exactly. So whenever we encounter a really highly specific, maybe seemingly pedantic requirement in this code, we have to look past the dry text. We have to ask what specific physical or chemical nightmare forced engineers to actually codify it.
Right, the real-world application. But before we get into the explosions and the disasters, let's set the boundaries right out of the gate.
Sure. So Chapter 1, Section 1.1.1 restricts our scope to stationary liquid fuel burning appliances.
Okay, so what does that actually mean for the listener?
It means we're looking at industrial, commercial, and residential type steam, hot water, and warm air heating systems. This isn't about, internal combustion engines or vehicles.
We're dealing with boilers, furnaces, and just massive commercial space heaters.
Exactly. And a crucial piece of context that often turns into a massive legal battle on job sites is Section 1.4. That deals with retroactivity.
Oh, man. Retroactivity is always a nightmare. Like, if you own a facility with an oil boiler that was installed in, say, 1985, and it met the code of the day back then, NFPA 31 is generally not retroactive, right?
Generally, yes. You aren't expected to totally gut your mechanical room every time a new edition of the code is published.
Right.
But if you look closely at Section 1.4.2, there is a massive caveat.
Always a catch.
Always. The authority having jurisdiction, the AHJ, which could be the fire marshal or the local building inspector, they hold the ultimate trump card.
Which is what?
It's the unacceptable degree of risk clause.
Oh, wow. Okay, so they can just walk in and say, nope, this is too dangerous now.
Pretty much. If the AHJ walks into a facility, looks at a grandfathered installation, and identifies an imminent hazard to life and property based on, modern understanding of fire dynamics, that grandfathered status just vanishes instantly.
They have the unilateral authority to mandate retroactive compliance.
Yes, they do. And let me give you a scenario that happens frequently.
Yeah, please.
So a building owner upgrades their 1980s facility with a highly efficient, hermetically sealed building envelope.
Oh, like spray foam insulation, triple pane windows, airtight vapor barriers?
Exactly. The building is now essentially a vacuum thermos. It's totally sealed.
Which is great for energy efficiency.
Great for energy, terrible for the boiler. Suddenly, that 1980s boiler, which totally relied on the drafty nature of the old building to pull in combustion air, is just suffocating.
Ah, I see.
So the AHJ comes in and points out that the operational environment has changed so drastically that the old system is now an unacceptable risk for carbon monoxide generation.
Because it can't breathe. That perfectly sets up where we need to start our deep dive. Because before we even look at the petroleum, the piping, or the burner, we have to deal with the lungs of the entire operation.
Yes, Chapter 5.
Right, Chapter 5 dictates the requirements for combustion air and ventilation. And this is arguably the most fiercely contested battleground between modern architectural goals and fundamental thermodynamics.
It really is. You have architects trying to build these tightly sealed, hyper-efficient envelopes, and then you have the mechanical and fire protection engineers demanding massive holes in those exact same walls so the fire can breathe.
Right. And you said this is the most common oversight you see in design reviews, right?
Absolutely. A massive oil-burning appliance requires a continuous, just staggering volume of air to achieve complete combustion.
So how does the code handle that?
Well, Section 5.3 draws a rigid line between unconfined spaces and confined spaces, and the volumetric threshold is absolute.
Give me the math.
It's 50 cubic feet of room volume per 1,000 B2 per hour of the aggregate input rating of all appliances in that space.
Okay, let's break that down for a second. Taking a standard residential or like light commercial input of, say, 100,000 B2 per hour, that math scales up aggressively.
It really does. You multiply that by 50, and the code demands 5,000 cubic feet of volume just to classify the space as unconfined.
Wow. So in a standard mechanical room with an 8-foot ceiling, you are looking at a 25 by 25-foot footprint completely dedicated to letting that boiler breathe via what the code calls normal infiltration.
Which brings us back to that fiction with modern architecture, because Section 5.3.2 specifically calls out that if normal infiltration is insufficient due to tight construction, like we talked about earlier, you are mandated to bring air directly in from the outdoors.
So what happens if a contractor messes that up? If you trap an oil boiler in a confined sealed space without dedicated outside air?
It gets dangerous very quickly. The chemical equation of combustion just breaks down. The appliance enters fuel-rich, oxygen-poor combustion.
Okay, so it starts running rich.
Right, and it generates heavy, oily soot that immediately coats and insulates the heat exchangers, which destroys the efficiency. But far more dangerously, it begins pumping out lethal concentrations of carbon monoxide.
Which is terrifying. And it sets the stage for a physical explosion too, right?
Oh, absolutely. If the chamber is flooded with vaporized, unburned fuel because there just isn't enough oxygen to sustain the flame, the environment inside the boiler is basically a bomb waiting for a trigger.
So someone simply opens the mechanical room door, allowing a sudden rush of fresh oxygen into that superheated, fuel-rich environment.
You get a violent delayed ignition, a puffback.
A puffback. That sounds almost harmless, but it's really not, is it?
Not at all. The concussive force can blow the flue pipe entirely off the boiler. It can blast the heavy steel doors right off the combustion chamber.
Good Lord.
Yeah, and it instantly fills the building with toxic smoke and potentially a structural fire.
Just because the room was too airtight.
Exactly. So to prevent that, Chapter 5 requires us to cut direct communication pathways to the outdoors. For a confined space, Section 5.4.2 mandates 2 permanent openings, one high, one low.
Okay, the high duct vents the ambient hot air out, right?
Right.
And the low duct provides the denser, fresh, oxygen-rich outdoor air to the burner intake. But looking at the sizing requirements for those ducts in the source material, the code reveals this fascinating aerodynamic reality.
The vertical versus horizontal duct rules.
Yeah. If you use vertical ducts, shafts running straight up through the roof, each opening must provide 1 square inch of free area per 4,000 BTU per hour.
Correct.
But then, Section 5.4.2.4 dictates that if you use horizontal ducts, say, running horizontally through the ceiling joist to an exterior wall, you need 1 square inch of free area per 2,000 BTU per hour.
It demands double the cross-sectional area.
Yeah, it doubles. I mean,
Right.
I'm assuming this is because horizontal runs entirely lose the benefit of thermal buoyancy. Is gravity really playing that big of a role in airflow?
That is the exact aerodynamic principle at play. In a vertical duct, you are basically harnessing the chimney effect.
Okay.
The slight heating of the air in the mechanical room creates a natural, powerful vacuum. The warm air rockets up the top vertical shaft, which mechanically pulls the heavy, cold outdoor air down the bottom shaft.
It acts as a natural pump.
Right. But the moment you turn that duct horizontal, you completely kill that vertical column of heavy air pushing down.
Oh, I see.
The airflow now has to drag itself horizontally, fighting profound static friction against the interior walls of the ductwork. So the code recognizes that the air is going to move sluggishly, and it forces you to build the highway twice as wide to compensate for the fact that the traffic is moving half as fast.
It's an elegant mathematical solution to a fluid dynamics problem.
I love that. And speaking of friction and obstruction, Section 5.6 brings up louvers and grills.
Oh boy, the louvers.
Right, because we know architects absolutely despise giant, gaping metal holes on the exterior of a beautiful facade.
They hate them.
They always want to cover them with decorative architectural louvers. But Section 5.6.3 drops a heavy restriction on calculating the required size. The code assumes a wooden louver only provides 25% free area, while a metal louver provides 75%.
And this is where theory meets reality. I have personally seen this fail in inspection, actually, on a multi-million-dollar commercial build. Wait, really? Tell me about that. What happened?
Well, the mechanical engineer calculated they needed exactly 100 square inches of intake air. So the contractor cuts a 10 by 10 inch hole in the exterior wall. Perfect, right.
Right, 10 by 10 is 100.
But then the exterior finish carpenter installed this tightly slatted, custom mahogany louver right over the opening to match the building's aesthetic.
Oh no. Because it's wood.
Because it's wood. Overnight, the functional airflow was choked down from 100 square inches to 25 square inches.
Because of the 25% rule in the code.
Exactly. So the boiler fired up, immediately starved for oxygen, triggered the carbon monoxide detectors, and completely shut down the facility.
All because of a pretty wooden louver.
Right. To get 100 square inches of actual breathable air through a wooden architectural louver, you have to cut a 400 square inch hole in the wall. You must size the opening based on the free area, not the gross area.
That is such a classic coordination failure between the architect and the MEP engineers. Okay, so let's say we survive the architectural louver disaster. The boiler has managed to take that massive breath of oxygen, the fuel atomizes, and the chemical reaction occurs.
Right.
But we can't just leave that reaction sitting there. We have a massive, high-temperature, highly corrosive exhaust. That brings us to the exhale.
Chapter 6.
Yeah, moving from Chapter 5 to Chapter 6. Venting of combustion gases. And this isn't just like warm air drifting away. The goal here is to shepherd toxic acidic gases from the combustion chamber to the outside atmosphere without leaking into the building or, igniting the structure.
And the primary vehicle for this is the chimney connector.
Which is what exactly?
It's the horizontal run of pipe that bridges the appliance to the vertical masonry or steel chimney. Section 6.5 governs this, and it contains one of the most critical never-do-this rules in the entire standard.
Ooh, I love the never-do-this rules. Let me guess, Section 6.5.2 explicitly states, a chimney connector shall not pass through a floor or ceiling.
That's the one.
Which, honestly, in a tight retrofit, I can easily see a contractor trying to bend this rule. Like the new boiler placement is across the basement from the chimney, and running a horizontal pipe is blocked by plumbing or ductwork.
It's very tempting.
The temptation to just run the connector straight up through the floor joists, maybe hide it inside a first-floor utility closet, and tap into the chimney higher up, must be huge.
It happens all the time, and the results are consistently disastrous.
Tell me why. Walk us through a scenario where a contractor actually does that.
Okay, first, a chimney connector is typically single-wall steel pipe. It operates at hundreds of degrees and requires massive clearances to combustibles.
Okay, so running it through a concealed floor joist bay is essentially packing a space heater against structural timber.
Right, which is an immediate fire hazard. But the more insidious threat lies in the chemistry of the exhaust itself.
What's in the exhaust?
Oil combustion gases are heavily loaded with sulfur dioxide. When those hot gases travel down a long connector, they begin to cool.
Makes sense.
If the temperature drops below what Section 3.3.2.1 identifies as the acid dew point, the sulfur compounds condense with the moisture in the exhaust to form liquid sulfuric acid right inside the pipe.
Wait, liquid sulfuric acid. So the pipe is literally digesting itself from the inside out.
Precisely. The acid eats through the single-wall steel relentlessly. This is exactly why Section 6.5.1 SIP mandates that the entire length of the chimney connector must be accessible for inspection, cleaning, and replacement.
Okay, so let's go back to that contractor who hid the pipe inside the floor cavity.
Right, so imagine that. 3 years later, the acid rusts a massive hole through the top of the hidden pipe. It's totally invisible from the basement because it's up in the floor joists.
Oh, man.
Now, every single time the boiler fires, it is pumping raw carbon monoxide and sulfuric vapors directly into the floor cavity.
Which just seeps right up into the bedrooms above.
Exactly. It transforms a mechanical oversight into a lethal, invisible gas chamber.
That is a terrifying reality check on why these rules exist. You walk into a house and you don't even know that pipe is in the floor.
You'd never know until it's too late.
So to keep those gases moving fast enough to avoid that acid condensation in the first place, Section 6.5.1 OR dictates that the chimney connector must maintain a continuous pitch or rise of at least 14" per foot.
Yes. The horizontal run is never truly horizontal.
Right. It has to act like an upside-down water slide.
That's a good analogy.
Like if a water slide has a flat spot, the rider loses momentum and gets stuck. With hot exhaust gases, which naturally want to rise, any flat spot or dip in that pipe kills their momentum. The thermal draft breaks down.
And instead of a stuck rider, you get corrosive acids pooling in the sag, accelerating the rust, and the exhaust gases just back up, spilling out of the draft regulator and flooding the mechanical room.
Speaking of the draft regulator, that's another component that requires absolute precision, right? Found in Section 6.4.
It does. The draft regulator manages the vacuum inside the flue, because the draft pulling the exhaust up the chimney fluctuates wildly based on barometric pressure, outdoor temperature, wind speed.
So it's constantly changing.
Constantly. Too much draft, and the fire is pulled too forcefully, burning inefficiently and potentially damaging the heat exchanger. Too little draft and the exhaust stalls.
So how does the regulator fix that?
It's a weighted, swinging barometric damper right on the connector pipe that swings open to pull ambient room air into the chimney, stabilizing the vacuum.
It's basically a mechanical pressure relief valve operating in reverse.
That's exactly what it is. But it only works if the integrity of the pipe is flawless. Which brings us to section 6.5.14, requiring each joint of the chimney connector to be fastened with at least 3 screws.
3 simple sheet metal screws per joint. That seems almost too simple. Does anyone actually mess that up?
Oh, absolutely. I actually recall a near-miss incident in a commercial greenhouse where the installer opted to use heavy-duty foil tape instead of screws to join the connector sections.
Foil tape. Why?
They thought it provided a better air seal. And honestly, it might have initially, but an industrial oil burner creates immense acoustic and physical vibration every single time it ignites.
The vibration.
Yes. So over a single winter, the constant thermal expansion, contraction, and violent vibration completely fatigued the tape. The joint cleanly separated.
Oh, wow.
The draft was instantly severed. And because the facility lacked a secondary spill switch interlock, the burner just continued to run.
So it was just venting straight into the greenhouse.
Yes. Venting thousands of cubic feet of combustion gas directly into the workspace until an employee collapsed.
Jesus. So 3 little screws literally prevent the system from rattling itself apart.
That's all it takes. Just follow the code.
The physical realities of this system are staggering when you really dig into it. So we've pulled the air in and we've forced the exhaust out. Now we must deal with the fuel itself.
The magma in your basement volcano.
Exactly. Where does this dormant volcano store its fuel? We are diving into Chapter 7, which dictates the physical footprint of the fuel storage. And this is where the code heavily intersects with structural and architectural planning, right?
It does, because storing concentrated liquid energy is strictly regulated by volume. The larger the volume, the more catastrophic the potential kinetic release.
Makes sense.
Section 7.5 governs tanks installed inside buildings, and 7.5.6 establishes a critical threshold. An unenclosed tank cannot exceed 660 gallons.
Okay, so if I have 2 standard 275-gallon oval steel tanks and I manifold them together in the open corner of a residential basement, that's perfectly fine, right?
Yes. So 550 gallons, which is well under the 660-gallon limit, assuming your clearances to combustibles are met.
But what happens when you were designing, say, a hospital, a large school, or an industrial facility? They can't rely on 275-gallon tanks. A winter deep freeze in the Northeast would drain that in days. They need 2,000, maybe 5,000 gallons of storage right inside the building footprint.
And that exact requirement is what triggers Section 7.6, dedicated tank rooms.
Dedicated tank rooms. Sounds expensive.
Very. If you exceed 660 gallons indoors, you are no longer just installing a tank, you are essentially building a fortified bunker.
A bunker.
Yeah. Depending on the aggregate size of the tanks, this dedicated room requires heavily rated fire-resistive walls, ranging from a 1-hour to a 3-hour fire rating, completely separating the fuel from the rest of the structure.
And the most physically demanding aspect of that bunker, at least from what I saw, is found in Section 7.6.1. The doorway to this dedicated tank room must be equipped with a non-combustible liquid-tight siller ramp at least 6 inches high.
That's the big one.
So if you're the AHJ walking a commercial site and you see a massive tank sitting in a mechanical room with a standard flush door threshold, you know instantly the code has been violated.
Immediately. The intent behind the liquid tight seal is absolute containment of a worst-case scenario.
A massive leak.
Right. If a 2,000-gallon tank suffers a catastrophic weld failure or a valve is sheared off by a forklift, the liquid fuel cannot be allowed to flow out into the adjacent corridors, down elevator shafts, or into floor drains leading to the municipal sewer.
But wait, looking at the math here, a standard 6-inch sill might not even be enough, right?
It rarely is for large tanks.
Because the code explicitly states the sill must be sized to contain a volume equal to the tank capacity. Let's actually run the numbers on this for the listener.
Let's do it.
Say an architect provides a dedicated tank room that is 10 feet by 10 feet. That gives us 100 square feet of floor area.
Okay.
A cubic foot of heating oil is roughly 7.5 gallons. So a 6-inch deep pool, half a foot across 100 square feet, is 50 cubic feet. Multiply that by 7.5, and a 6-inch sill in that specific room will only hold back 375 gallons of liquid.
Which highlights exactly the problem. If the tank in that room holds 1,000 gallons, a 6-inch sill is utterly useless. The oil will overflow the sill by over a foot.
Over a foot of oil just spilling out the door.
Yeah. To contain 1,000 gallons in a 10 by 10 room, that liquid-tight sill has to be nearly 18 inches high.
18 inches. It ceases to be a threshold and becomes a small dam.
A literal dam, and you can imagine how this severely complicates maintenance access. It requires heavily engineered ramps for equipment removal, and it fundamentally alters the architecture of the space.
It proves that you cannot treat a commercial mechanical room as an afterthought. The physics of volumetric containment actually dictate the architecture.
Completely. And while a 1,000-gallon spill is a massive environmental disaster, a spill that actually finds an ignition source is a structural catastrophe.
That's the purpose of the 3-hour fire-rated doors.
Exactly.
But what actually causes these tanks to rupture in the first place? Besides a forklift hitting them, Section 7.2.5 sheds light on a mechanism that seems totally counterintuitive to me: tank openings for fill and venting.
This is a critical, high-stakes safety mechanism that is deeply misunderstood by inexperienced installers.
How so?
Every fuel tank requires a fill pipe for the delivery truck to attach to, but it is equally mandated to have a vent pipe terminating to the outdoors. The massive oversight happens when people assume an empty tank is actually empty.
But it isn't. It is completely filled with atmospheric air and fuel vapors.
Right, so when a commercial delivery driver hooks up a high-pressure hose and begins pumping 80 gallons of dense liquid oil into that tank every single minute, an equal volume of air has to be evacuated instantly.
Instantly.
Yes.
Tell me what happens if that vent pipe is compromised. Let's walk through a story on that.
Okay, imagine a scenario where the vent pipe was undersized by the contractor, or maybe it's been blocked by an ice storm or a wasp nest over the summer.
A wasp nest.
Hmm.
Unbelievable.
It happens. The tank is violently transformed into a pressure vessel. Standard atmospheric heating oil tanks are geometrically and structurally incapable of handling internal pressure.
Because they're basically just flat steel boxes.
Exactly. The massive surface area of the flat steel sides means that even a minuscule increase in PSI translates to thousands of pounds of outward kinetic force.
And the pump on the delivery truck isn't going to stall, right? It's industrial. The pressure simply builds until the weakest point yields.
Correct. The welded seams of the steel tank will literally zipper open with the sound of a gunshot.
Zipper open.
Yes. Hundreds of gallons of oil will explosively spray across the room before the driver outside even realizes there's a pressure spike.
That is insane.
And this is why Table 7.2.5.1 rigidly links the minimum diameter of the tank vent to the total capacity of the tank. A standard residential tank demands a minimum 1 and 14-inch vent pipe. A massive commercial tank might require a 2-inch or larger vent.
Furthermore, Section 8.6.2 dictates these vents must terminate outside above the maximum anticipated snow line, equipped with weatherproof caps. The simple geometry of a vent pipe is the only thing standing between a routine fuel delivery and a massive hazmat response.
It's all connected.
The interdependent physics of these systems are incredible. Okay, so the fuel is secured in its bunker, it's perfectly vented, it's contained behind a structural sill. Now we have to move that fuel to the burner.
The arteries.
We are moving into the arteries. Heating, fuel piping, and valves under Chapter 8. The pipes are carrying a concentrated flammable liquid through the occupied space, so the metallurgy and fail-safes have to be intensely regulated.
Section 8.2 outlines the acceptable materials. Minimum Schedule 40 steel pipe, brass pipe, or specific thick-walled copper tubing.
But it is Section 8.3.4 that delivers one of the most blunt and uncompromising mandates in the entire code. Cast iron fittings shall not be used.
The cast iron ban.
Yeah, and coming from a plumbing perspective, this seems so strange to me. Like, we use cast iron for gravity drains and sewer lines constantly. It lasts for a century. Why is it strictly banned for fuel oil?
It comes down to the metallurgical differences between handling water and handling volatile fuel.
Okay, explain that.
Cast iron is exceptionally strong in compression, but it has almost zero tensile strength and no plasticity.
Plasticity. Even it doesn't bend.
Exactly. It does not bend. It fractures. It is incredibly brittle.
So if a pipe gets bumped, it doesn't just dent like copper would.
Right. I actually read a case study of an industrial retrofit where a contractor ignored the cast iron ban on a primary fuel line.
Oh boy. What happened?
A mechanic was working above the line and accidentally dropped a standard steel pipe wrench.
Just a wrench.
Just a wrench. It wasn't even a massive impact, but it struck the cast iron elbow fitting. And because it lacks plasticity, the cast iron developed a microscopic hairline fracture.
Which you probably couldn't even see with the naked eye.
You couldn't. So over the course of the weekend, while the shop was closed, 300 gallons of diesel silently bled through that invisible crack, soaking into the concrete and floor drains.
Wow.
Furthermore, in the event of a room fire, Cast iron suffers terribly from thermal shock.
Oh, because of fire sprinklers.
Yes. If the fitting is superheated by a localized fire and is suddenly hit by cold water from a fire sprinkler system, the cast iron will shatter like glass.
It just shatters.
Just bursts. So
Yeah.
suddenly, a small containable trash fire breaks the primary fuel line, and the entire contents of a 500-gallon tank gravity feed directly into the flames.
So piping oil requires a level of physical fail-safes that standard plumbing doesn't even have to consider.
That's right.
And that actually brings us to what might be the most elegant piece of analog engineering in the entire NFPA code: the fusible link safety shutoff valve.
Found in Section 8.7.2.
Yes, I love this thing.
It is the ultimate unsung hero of fire protection. The code mandates a readily accessible automatic safety shutoff valve to be installed as close as practical to the burner and immediately upstream of the fuel filter.
Looking at Section 8.7.2, these valves are incredible to me because they rely on absolutely zero electronics. There are no Wi-Fi signals to drop, no smoke detectors to fail, no control boards that can short out. It looks like pure localized metallurgy.
Pure analog engineering.
They use a specific bismuth alloy link that is chemically engineered to melt at exactly 165 degrees Fahrenheit to trigger a spring, right?
Spot on. It is a purely analog physical failsafe.
Walk me through exactly how it works in a fire.
So the spring-loaded handle of the valve is held open under extreme tension by that tiny bismuth alloy link.
Why bismuth and not just regular solder?
The reason they use bismuth alloys rather than standard lead-tin solder is that bismuth provides a sharp, precise melting point rather than slowly softening over time. So if a malfunction occurs, say the burner casing cracks and flames start licking the exterior of the unit, or a rag left on the boiler catches fire at the ambient temperature directly above the valve spikes.
And then?
The precise millisecond that ambient air hits 165 degrees, the bismuth link simply ceases to exist structurally. It melts away.
The tension is instantly released.
The heavy internal spring slams the brass valve shut with a loud mechanical clack. The fuel supply is permanently and physically severed.
So the fire might consume whatever residual oil was in the filter or on the floor, but the main volumetric supply from the 1,000-gallon tank is completely cut off.
Exactly.
Which highlights the absolute tragedy of human interference with these systems.
Don't even get me started.
If an installer forgets to put in that $50 valve, or worse, if a maintenance technician gets annoyed by a weak spring and props the valve open with a nylon zip tie.
Which happens all the time.
Really, a zip tie.
I've seen it more times than I can count. They have fundamentally disabled the system's survival mechanism. A localized, totally survivable fire is now continuously fed by a high-pressure stream from the main tank until the building burns to its foundation.
Exactly. The reason Chapter 8 is completely unforgiving. Every component is engineered with the assumption that a failure will eventually occur, and the system must be physically forced to fail safely.
That's the core philosophy of the NFPA.
All right, so we have the air intake, the exhaust draft, the bunker, and the arteries. The fire is now successfully and safely burning inside the combustion chamber of the appliance. Now we have to manage the intense thermal radiation blasting outward into the room.
Clearances.
We are looking at clearances to combustibles in Chapter 10. How do we keep the appliance from simply igniting the walls around it?
Well, heat transfer is relentless. An oil burner generates immense radiant and convective heat. The final, ultimate line of defense between the steel casing of the appliance and the combustible structure of the building is sheer physical distance.
Right, looking at Table 10.6.1, clearances to combustible material, the code categorizes appliances by form, Roman numerals I through V.
Correct.
Form I is your basic residential warm air furnace. It asks for a modest 2 inches of clearance above, 24 inches in front for maintenance access, and 6 inches on the sides. Pretty reasonable, but when you jump to Form 4, the requirements are staggering.
Form 4 represents a medium heat industrial appliance. Think of a massive, high-pressure steam boiler or an industrial process heater.
And what are the clearances for that?
The code demands 48 inches of open clearance above it, 96 inches, a full 8 feet of clearance in front of the burner, and 36 inches, a full 3 feet of dead space on the sides and rear.
Imagine being the mechanical engineer trying to shoehorn a Form 5 boiler into a cramped legacy basement in downtown Manhattan.
It's an absolute nightmare.
You simply might not have 36 inches on the sides to give without hitting a structural wooden column.
Yeah.
If you only have 12 inches of physical space, do you just fail the inspection? Is the project dead?
This is where the code offers an incredibly precise engineering workaround. Table 10.6.2, reduction of clearances.
Okay, how did that work?
Engineering allows us to mitigate radiant heat transfer, but only if we strictly obey the laws of thermodynamics.
Okay, let me play the role of the corner-cutting contractor here.
I love this.
I install my boiler, and I realize the steel casing is only 12 inches away from combustible wooden stud wall instead of 36. The inspector is going to flag the missing clearance. Can't I just run to the hardware store, buy a sheet of 24-gauge galvanized steel, and literally just nail it directly to the wooden studs? The metal obviously won't burn. It will block the radiant heat. Code satisfied, right?
That exact logic is responsible for slow-burning structural fires every single winter.
Wait, really? But metal doesn't burn.
If you nail a piece of sheet metal directly to a wooden stud, you haven't stopped the heat, you've just built a highly efficient frying pan.
A frying pan.
Yes, the metal is non-combustible, sure, but metal is a phenomenal conductor of thermal energy. Ugh. It absorbs the radiant heat from the boiler and just aggressively mainlines it straight into the wood.
And what happens at a molecular level to that wood behind the metal is terrifying. It is a chemical process called pyrolysis.
Pyrolysis, explain that.
Over months and years, as the boiler cycles on and off, it exposes that wood to sustained baking temperatures of 200 or 250 degrees Fahrenheit. The metal traps the heat, accelerating the process.
So it's literally baking the wood slowly.
Exactly. The wood's chemical structure fundamentally breaks down. It desiccates entirely, it off-gasses its volatile moisture, and its auto-ignition temperature just plummets.
Auto-ignition temperature, like the temperature where it catches fire without a spark.
Right. Standard framing lumber usually ignites around 500 degrees. Pyrolyzed wood can spontaneously ignite at 250 degrees.
Oh my God.
So eventually, on a freezing Tuesday in February, when the boiler has been running at maximum capacity for 14 hours straight, that degraded wooden stud will just spontaneously burst into flames right behind the metal plate.
It is an invisible slow-motion time bomb. It's structural sabotage masquerading as fire protection.
That is wild. Okay, so how does Table 10.6.2 actually instruct us to safely reduce that clearance?
The absolute non-negotiable requirement is a ventilated airspace.
Ventilated airspace.
Yes. Looking at option C in the reduction table, 0.024-inch sheet metal, which is standard 24 gauge. If you install that metal over 1 inch of glass fiber insulation and crucially leave a 1-inch ventilated airspace between the protective assembly and the combustible wall,
Wait, hold on. How do you securely mount a heavy sheet of metal if it has to float an inch off the wall?
you use non-combustible spacers, like staggered ceramic standoffs or sacked steel washers, but you never place those spacers directly behind the heat source where they can act as conductive thermal bridges.
So you secure it at the edges.
Right, you secure the assembly at the extreme edges. And the critical mechanism here is that the 1-inch space behind the sheet metal must be completely open and unobstructed at both the bottom and the top.
Ah, we're harnessing the chimney effect again, just like the vertical ventilation decks from Chapter 5.
Spot on. It is pure convective cooling.
Walk me through the physics of that.
The radiant heat from the boiler aggressively heats the face of the sheet metal. The metal heats the 1-inch pocket of air trapped directly behind it. Because hot air is lighter, it rapidly rises and escapes out the top opening.
And as it exhausts.
It creates a vacuum that powerfully pulls cool, heavy room air in from the bottom opening. It creates a continuous high-velocity river of cold air rushing between the superheated metal and the combustible wood.
So the thermal energy is convected away into the room before it ever has the chance to conduct into the structure.
Exactly.
That is thermodynamic brilliance. By utilizing 24-gauge sheet metal with a continuously ventilated airspace, Table 10.6.2 allows you to drop a massive 36-inch clearance requirement all the way down to 12 inches safely.
You just bought back 2 feet of usable floor space.
But if a contractor skips the airspace because they want the metal to sit flush and look aesthetically pleasing, they've guaranteed a pyrolytic fire. You cannot cheat the physics of heat transfer. The code merely tells you how to manage it.
Which actually serves as a perfect transition into an area where human ingenuity desperately tries to cheat the system. Alternate fuels.
Oh, this is the Wild West.
It really is. Up to this point, our entire discussion has been predicated on the assumption that the fluid in the tank is pristine, commercially refined, highly predictable number 2 heating oil.
Right.
But out in the field, thriftiness often overrides common sense. People try to burn whatever viscous fluid they have lying around.
We are diving into the wild cards, chapters 11, 12, and 13, covering used oil and portable heaters. Let's look at a common scenario that I think a lot of people might actually encounter.
Go for it.
A commercial trucking company has a fleet of diesel rigs. They generate hundreds of gallons of drained crankcase oil every single month. Can the owner just pipe that waste oil into the warehouse boiler to save on heating costs?
Well, Section 4.5.2 draws a massive, uncompromising red line here based on occupancy. Used oil or crankcase oil shall not be used in a residential occupancy, period.
Okay, but what about the warehouse?
It is permitted in commercial or industrial settings like that trucking warehouse, but under extreme scrutiny.
Why this strict ban on residential, but a conditional pass for commercial garages? What makes waste oil so inherently dangerous compared to heating oil?
It all comes down to the volatility of the flash point.
Flashpoint.
Yes, standard number 2 heating oil is incredibly stable. Its flash point is reliably high, well over 100 degrees Fahrenheit.
Meaning it's hard to light on fire.
Right. If you drop a lid match into a bucket of cold heating oil, the match just goes out. It requires intense mechanical atomization to burn. But used crankcase oil is a complete chemical mystery.
Because it's been in an engine.
Exactly.
Yeah.
When a mechanic drains oil from a truck, what else ends up in that 50-gallon drum?
Everything. Little residual gasoline, some volatile brake parts cleaner, maybe some paint thinner or degreaser swept off the floor.
Exactly. Solvents, gasoline, antifreeze. When you introduce even a small percentage of highly volatile solvents into the heavy oil, you drastically alter the chemical profile.
So it's not just oil anymore.
No. Section 4.6.2 specifically warns about this contamination. If a batch of used oil has a combined flash point that drops below 100 degrees Fahrenheit, it is no longer just a liquid. It is actively generating highly flammable, invisible vapors at standard room temperature.
Oh, wow. So instead of a tank holding a thick, stable puddle of oil, you have a tank that is off-gassing an explosive vapor cloud right into the surrounding room.
Precisely. If you place a tank of contaminated used oil in a residential basement right next to a gas water heater with an open pilot light, boom.
You don't get an oil fire, you get a localized vapor explosion.
Yes. Commercial garages are permitted to use it because their mechanical ventilation rates are massive, ceiling heights are cavernous, and the ambient environment is heavily controlled.
Right.
But even then, burning it is an engineering nightmare. Section 12.7 outlines intense regulations for the burner's atomization air supply and the mandatory preheating of the oil.
Let's dive into the physics of atomization for a second. Why does the code mandate preheating for used oil but not for standard heating oil?
Because a burner does not actually burn liquid oil. It burns oil vapor.
Okay.
To achieve that rapid vaporization, the mechanical nozzle has to shatter the heavy liquid into millions of microscopic droplets, exponentially increasing the surface area exposed to the ignition spark.
So standard heating oil is thin enough at room temperature to shatter perfectly.
Yes. Used oil is incredibly viscous. It's thick, cold sludge. If you pump cold crankcase oil into a standard nozzle, it won't shatter. It will just squirt a heavy, unignitable stream of sludge straight into the back of the combustion chamber.
It just makes a mess.
So the system has to mechanically preheat the oil, sometimes pushing it well over 150 degrees, strictly to drop the viscosity low enough so the physics of atomization can actually take place.
But wait, here is the razor's edge. If you heat the oil to thin it out, but that oil contains the hidden, highly volatile solvents we just talked about.
Yes.
The solvents will boil inside the fuel line.
Exactly. The solvents flash into gas inside the enclosed piping, creating vapor lock.
Oh.
The pump loses its prime, the burner surges erratically, and you risk a premature ignition inside the burner tube itself.
That sounds like a disaster waiting to happen.
It is. The entire apparatus, the specialized pumps, the heavy-duty atomizers, the calibrated safety controls, must be meticulously engineered to handle wild chemical unpredictability. Oil is not a single monolithic substance.
When you alter the chemistry of the fuel, you fundamentally alter the physics of the fire, and the code has to build incredibly robust guardrails to manage that chaos.
Absolutely.
And briefly touching on another wild card, Chapter 11 governs portable, unvented kerosene heaters, the kind you buy at a big box hardware store.
Unvented room heaters are treated with extreme caution by the NFPA.
Because they lack a chimney connector, right?
Right.
100% of the combustion gases, including moisture, carbon dioxide, and trace carbon monoxide, are exhausted directly into the occupied living space.
Right. Section 11.2 dictates strict rules for clearance to combustible drapes and leveling, but Section 11.2.7 is honestly the most critical. The filling of the removable fuel tanks must be performed outside the building.
Because attempting to pour highly refined kerosene into a small tank inside a carpeted living room right next to a piece of metal that was just glowing cherry red 5 minutes ago.
Is inviting a structural fire through sheer human clumsiness? The code is trying to legislate human error out of the equation as much as mathematically possible.
Let's pull all these complex threads together for the listener. We've taken a massive journey through the physical and chemical realities of NFPA 31 today.
It's a lot to take in.
It is. We started by examining the lungs of the system in Chapter 5, proving that a boiler trapped in a tightly sealed modern building will suffocate, generate lethal carbon monoxide, and potentially cause an explosive puffback if we don't calculate the precise aerodynamic requirements for vertical and horizontal ventilation ducts.
And watch out for those wind louvers.
Yes. We looked at the exhale in Chapter 6, where we saw how the acid dew point creates sulfuric condensation that will literally digest a hidden chimney connector, and why 3 simple sheet metal screws are the only thing preventing a draft failure.
We explored the belly of the beast in Chapter 7, breaking down the volumetric math of liquid-tight sills and the terrifying reality of a tank zippering open if a vent pipe is undersized during a delivery.
We followed the arteries through Chapter 8, where the brittle metallurgy of cast iron makes it a deadly hazard in a fire, and the elegant analog physics of a melting bismuth alloy fusible link acts as the ultimate failsafe.
And we tackled the intense thermal radiation in Chapter 10, discovering the invisible threat of wood pyrolysis and the thermodynamic brilliance of a ventilated airspace.
And finally, we looked at the chemical wildcards of used oil, where volatile solvents and viscosity dictate a razor-thin margin of safety for atomization.
We covered a lot of ground.
For me, the ultimate revelation here is that NFPA 31 is far more than just a fire code. It is a masterclass in multidisciplinary coordination.
Oh, 100%.
If the mechanical engineer sizing the BTU input, the architect designing the hermetically sealed envelope, and the fire protection engineer calculating the volumetric containment of the tank room are not communicating flawlessly, the system will fail.
The code is the uncompromising language they must use to force their disciplines to acknowledge each other's physical realities. You cannot design a beautiful, flush interior wall without acknowledging the thermodynamic reality of a 36-inch clearance.
It acts as the ultimate referee between architectural aesthetics, mechanical efficiency, and the unforgiving laws of thermodynamics.
It really does.
So, to you, the listener, the next time you are walking a job site, inspecting a commercial mechanical room, or even just looking at the furnace in your own basement, look with X-ray vision.
Look at the details.
Look at the free area of the louvers on the door. Look for the mandatory 14-inch pitch on the silver chimney pipe. Look for that little spring-loaded brass valve sitting upstream of the fuel filter. You now possess the insight to understand exactly why they are designed the way they are and the catastrophic disasters they are silently preventing every single day.
And as we close the book on this deep dive, it leaves us staring down an incredibly complex, high-stakes question for the future of building infrastructure.
How's that?
Well, NFPA 31, with all its precise tables and hard-won safety margins, is exquisitely tuned to the specific chemical and physical behaviors of legacy petroleum distillates.
Standard number 2 heating oil, kerosene, fuels pumped from the earth.
Yes. But the energy landscape is shifting rapidly. The industry is aggressively pivoting toward decarbonization.
Oh, right.
We are seeing the rapid introduction of synthetic fuels, complex biodiesel blends like B20 or B100, and advanced biofuels derived from agricultural waste or algae.
And those are completely different mechanically.
Absolutely. These 21st century fuels are chemically distinct. They possess different flash points. Their viscosity curves under temperature changes are completely different. And critically, they interact chemically with legacy rubber gaskets, pump seals, and copper piping in ways that standard petroleum does not.
Wait, they might degrade the very fail-safes designed to contain them.
Exactly. So as we inevitably begin pumping these modern sustainable fuels into millions of gallons of 20th century infrastructure, will the foundational physical assumptions underpinning NFPA 31 still hold up?
That's a scary thought. Will the volumetric expansion rates inside the tanks remain safe? Will the corrosive sulfur profile change, accelerating the deterioration of our chimney connectors in unexpected ways?
Exactly. How do engineers and the AHJ retrofit a century of blood-written fire code to safely manage a suite of complex chemical fuels that literally did not exist when these safety rules were first carved into stone?
That is a phenomenal, unsettling thought to leave on. The physics of fire and heat transfer will never change, but the chemical makeup of what we feed that fire is evolving faster than the code itself. We will have to watch closely to see how the engineering community adapts to keep those dormant volcanoes safely contained. Thanks for joining us on this deep dive.